Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 30, and we are going to continue with our discussion on energy methods from the last lecture. Okay. So, the first thing to learn today is what is called Castigliano's theorem. Castigliano's theorem, and there are actually many, first, second, third, and we are going to talk about just the first Castigliano theorem. Okay. So, we have derived the expression for energy as summation over all the forces, and actually now the generalized forces, half of F I into delta I, right, where F I is the generalized force, which could also be moment, and delta I is the generalized displacement, which can be both displacement or rotation. All right. And then we also saw that we could write it completely in terms of forces. So, for that we replaced delta I in terms of force as k I j f j, right, and the whole thing then becomes half k I j f I f j, and we have double summation here. So, that is the energy expressed in terms of generalized force. Now, let us see what is the first derivative of this energy with respect to the generalized force. All right. So, del E over del F k, for example. See, we should not use I and j because they are already being used here. So, del E by del F k is then summation over I j, that is half k I j del F I over del F k into F j plus F I del F j over del F k, okay, which is then equal to half double summation k I j into delta I k, del F I over del F k is delta I k into F j plus F I into delta j k, right. And then this also, you see, we have delta I k and we have summation over I. So, the I summation will be annihilated, and wherever we have I has to be replaced with k. So, this becomes half summation over j k k j f j. So, that is the first term, and for the second term we have delta j k. So, summation over j is going to be annihilated and j will be replaced with k. So, we have summation over I k I k f I, right. And then you see the first term we have summation over j and then summation over I, but the index of summations, they are dummy. So, we could replace j with I. So, this becomes half summation over I k k I f I plus k I k f I, is not it? And then we use reciprocal relation, which is that k k I is same as k I k. So, this half will then be gone, is not it? And we simply have summation over I k k I f I. And can you see what is this? This is nothing but the corresponding displacement delta k, right. So, we have proved a very interesting relation, that the corresponding displacement delta k is the derivative of the energy with respect to the corresponding force F k. Okay. So, delta k is nothing but del E over del F k. Simply have to make sure that we write the energy in terms of the forces, so that we can take the proper derivative with respect to force. All right. So, that is the Castigliano's first theorem, and you will see that this is going to be very useful while finding out displacement or rotation, which is like a generalized displacement, right. So, without solving the Euler-Bernoulli or Timoshenko beam theory, we could simply write the energy of the beam in terms of the applied load and take the derivative to get the corresponding displacement. All right. Okay, so, what we see is that writing down the expression of energy is really critical here, then only we can use these theorems, right. So, let us think of a 3D body. So, we have a 3-dimensional body which could be clamped again at some points. Then what is the energy stored in the body? If we assume that stress and strain are linearly related, then the energy stored E becomes integration over the volume of the body into half of sigma I j times epsilon I j into dV. Okay. So, that is the energy stored in the body. Now, this is for a 3-dimensional body. You know, we are going to apply this energy method mostly for beams. So, is it possible to write this energy as a 1-dimensional integral over the length of the beam? So, suppose that we have this beam, so this beam has got the length L and also the cross section, right, omega. So, as we vary the cross section, we go through the entire volume of the beam. So, this volume integral here could also be written as integration over the length 0 to L ds, S for the arc length, and then the integration over the cross section omega, right, half sigma I j epsilon I j into d omega. Okay. So, if we split the volume integral into cross sectional integral and line integral, then we indeed have an integration over the length of the beam of this thing, which can be called as cross sectional energy, because we are integrating over the cross section the 3-dimensional strain energy density. So, this is cross sectional strain energy. Now, a beam deforms in various ways. It can undergo bending, it can undergo stretching, it can undergo shearing, it can undergo twisting, right. So, we have bending, torsion, stretching, shearing of beams. So, for each of these modes, we will have different forms of energy of the cross section of the beam, right. For example, think of simple extension of the beam. So, we have a beam which is being stretched by applying some axial load okay. Suppose that the net load is P here and it is uniformly distributed over the cross section, then what is the energy stored in the cross section of the beam? So, we have to first think of what is the state of stress and what is the state of strain. So, you can recall from the extension of beam, whenever we do extension with the cross section allowed to relax fully. So, in this case for example, there is nothing on the cross section, right. So, the cross section is traction free. So, it can relax freely. So, in that case the state of stress sigma has got only axial stress. So, suppose that this is 1, that is 2 and this is 3. So, 2 and 3 are in the cross section and 1 is along the axis of the beam, then we only have sigma 1 1 and rest all are 0. Okay. And for such a state of stress, what would be epsilon 1 1? You use 3 dimensional Hooke's law, that is 1 over E times sigma 1 1 minus nu times sigma 2 2 plus sigma 3 3, but this is 0. So, that is simply sigma 1 1 by E, correct. So, what is the cross sectional energy? The cross sectional energy is then integration over the cross section half sigma I j epsilon I j. Okay. And you have to remember that we have a double summation here actually over I and j. So, we have to sum over the different components of stress multiply with the same component of strain sigma 1 1 into epsilon 1 1 plus sigma 2 2 into epsilon 2 2. Likewise, you do it for all the components and then sum it. Okay. For the case of axial extension here, we only have sigma 1 1. So, the double summation simply is gone and we have half sigma 1 1 epsilon 1 1 into d omega, right. So, we have integration over the omega sigma 1 1 square by 2 E. And what sigma 1 1? If the total load is P, it is uniformly distributed, then sigma 1 1 is simply P by A. So, we get integration over the cross section P square over 2 E A square, right, d omega. Now, P, Young's modulus and the cross sectional area A, they are all independent of the cross section. So, it comes out of the integral and we have P square by 2 E A square integration over the cross section, which gives me again the cross sectional area. So, this is finally P square by 2 E A. Okay. So, the energy due to extension of the beam equals the axial load P in the cross section times its square divided by 2 times E A, and E A is nothing but the extensional stiffness of the beam. Okay. So, we can write here the energy due to extension equals P square by 2 E A, where P is the axial load and E A combined, E is a Young's modulus, A is the cross sectional area, but the combined, that is called axial stiffness, okay, or stretching stiffness, because we are doing actually the stretching of the beam. Okay. Now, then we have another mode that is called the bending. So, let us see what is the bending energy. So, in case of bending energy, a beam gets deformed into a circle, right, and if we have 1 here and again 2 and 3 in the cross section, then we can recall that the state of stress sigma has again got only sigma 1 1 and sigma 2 2 and sigma 3 3 are 0, because again the cross section is allowed to relax. So, recall from the pure bending of beams, state of stress had got only sigma 1 1 and there was no shear if it is a pure bending. Okay. Now, what is then epsilon 1 1? So, epsilon 1 1 or epsilon x x is simply minus of bending curvature kappa, right, times y, where y is the distance from the neutral axis, is not it? And what sigma 1 1? That simply E times epsilon 1 1. So, this is equal to minus E times curvature kappa into y, correct, and we also write this as minus m y divided by I z z, correct. Okay, so, what is the energy of the cross section now? So, we have integration over the cross section half of sigma 1 1 into epsilon 1 1 only, because rest all stress components are 0 into d omega. So, that is half integration over the cross section, and we have E into curvature square into y square d omega, right. So, half into E into curvature square, it comes out of the integral, and we have y square d omega, and that is by definition I z z, correct. So, this is half E I z z into curvature square, but we want to write this in terms of bending moment, right. Remember, we have to write down the energy of the beam in terms of what is acting in the cross section, the various forces and moments. So, right now it is in terms of curvature, let us try to write it in terms of bending moment. Okay. So, what is the curvature and moment relationship? You can recall that m z was E I z z times the curvature. So, if you plug it here, we simply have half E I z z into m z over E I z z whole square, correct. So, this becomes m z whole square divided by 2 times E I z z, all right, and E I z z is actually what is called bending modulus. Okay. See, this is bending energy, but looking at it from the 3D perspective, it is actually normal strain energy, because we have sigma 1 1 into epsilon 1 1. Sigma 1 1 is normal stress, epsilon 1 1 is normal strain. So, it is kind of normal strain energy, but for the cross section it looks as a bending energy. Notice also its similarity with the axial strain energy. So, have a look at this term. So, there we have p square by 2 E A, and in case of bending we have m square by 2 E I. So, for axial extension the force is p, therefore, we do p square by 2 times axial stiffness. For bending the force is bending moment, that is a generalized force, right. So, therefore, we do bending moment square divided by 2 into bending modulus. So, similarly, you can show that the energy due to torsion of the beam, so the torsional energy would then be T squared, the torque that acts in the cross section T, okay, divided by 2 into G j, because G j is the torsional modulus. Okay, so, that is the torsional modulus. And finally, we have shear energy, the energy due to shearing of cross sections. See, in torsion also the cross sections shear, but it is a different kind of shear. What kind of shear is present here? If you think of cylindrical coordinate system, so shear present here is due to torsion or torque, and that is gamma theta z. Okay. Whereas the shear energy due to transverse load, not due to torque. Whenever we have transverse force in the cross section, that is also going to generate a shear, and the shear stress there is such that the resultant force due to shear stress is the transverse load, whereas the resultant force due to shear by torque, that is 0. Okay. So, understand the difference between the torsional energy which is also due to shear and then the shear energy due to transverse load, and this then becomes the transverse shear force V square divided by 2 into shear stiffness, okay, and shear stiffness is G A, and then we also have a correction factor K, all right. So, basically when we have a beam, suppose it is clamped at one end, then we will have some force in the cross section which is the vector V, and some moment also in the cross section vector m, and the shear force V you can then decompose into 3 components, right. One along the axis V x, we will call it as P axial force, and then in the cross section V y and V z, okay, V y and V z. Likewise, for the moment m, we can resolve it into various components. The component along the axis, that is the torque, right. So, this is T, which is also m x, and the remaining components they are bending moments. So, we have m y and m z, and we know energy due to each of the 6 components separately, and then because we are working with linear elasticity, the energy when all of them work together would simply be the superposition of each of the energies, right. So, that means energy is stored in the beam equals half of integration from 0 to L P of x square by 2 E A plus m y of x square divided by 2 E I y y plus m z of x whole square divided by 2 E I z z plus the energy due to torsion T x whole square divided by 2 G j plus the energy due to shear force. So, that is V y of x whole square divided by 2 correction factor k G A plus V z whole square divided by 2 correction factor k G A, and the whole thing has to be integrated with respect to length dx. Okay. And notice that the first 3 terms here are actually the normal strain energy, whereas the last 3 here they are the shear strain energy, because they are due to shear. And to find the total energy of the beam, we simply have to integrate this over the length of the beam. And what is varying here are P x, m y, m z, T x, V y, V z. So, they could be varying along the length of the beam. All right. So, having done the theory, let us now work out some examples. So, first of all, let us think of a beam which is clamped at one end, and we are applying force at a distance a from the clamped end. Okay. So, we are applying a force F here, let us say F1, and our goal is to find out theta L, what is the rotation of the cross section at x equal to L, the tip rotation. Okay. So, we can of course do it in various ways. One is we directly solve the differential equation and obtain the tip rotation. So, if we do that, let us call this point here as point 1 and this as point 2. Okay. And let us try to use Euler-Bernoulli beam theory. So, if we do that, what is the deflection formula? E I d 2 y by d x 2 is equal to bending moment m, right. And in this case, we have force F 1 at A. So, the bending moment profile would then be bending moment is equal to 0 when x is greater than A, right, and this is equal to F 1 into A minus x when x is less than A. Okay. So, we can work this out by drawing the free body diagram. So, for x less than A, this becomes F 1 into A minus x when x is less than A, and let us do its integration. So, we have to integrate twice and we get the deflection. So, we have F 1 A x square by 2 minus F 1 x cube by 6 plus C 1 x plus C 2, okay, the integrating constants. Then we apply the boundary condition that at x equal to 0, y is equal to 0 and theta is also equal to 0, but theta is equal to dy by dx, right. So, when we apply that, C 1 and C 2 are both going to vanish. So, that means your deflection y is equal to F 1 by E I into a x square by 2 minus x cube by 6, okay. And the rotation, since it is an Euler-Bernoulli theory, rotation is same as dy by dx. So, theta is equal to dy by dx, which is equal to f1 by ei into ax minus x square by 2. But you have to remember that this formula holds only when x is less than equal to a. Okay. So, what is the theta when x is equal to a? So, theta when x is equal to a, you simply substitute x equal to a, and we have f1 a square divided by 2 e I. Okay, so that is theta of a, but what about theta of L? You see, in between x equal to a to x equal to L, the moment of x is equal to 0. So, from the Euler-Bernoulli equation, d2y by dx2 is equal to 0, which also means d theta by dx is equal to 0, which means theta is constant in this segment. Right. So, this then implies that theta of L is equal to theta of A and equal to f1 a square by 2 e I. If you think in terms of influence coefficient, then theta of L is actually theta 2, and that is equal to a square by 2 e I into f1. Okay. So, that is your k to 1. So, having obtained k to 1, can we check that k to 1 is equal to k 1 2? So, how to check k to 1 equals k 1 2, because that should hold from reciprocal relation. So, to obtain k 1 2, we then have to apply bending moment at 2 and measure deflection at 1, right, because it has to be reverse of k to 1. So, let us think of the beam, and we are applying a bending moment m at the end, and so here the bending moment will be constant all along, because it is the case of pure bending. So, that means E I d2y by dx2 is equal to m. So, deflection y is then 1 over E I into m x square by 2 plus C 1 x plus C 2, right, and then you apply the clamped boundary condition that at x equal to 0 deflection is 0 and rotation is also 0. That would mean that C 1 and C 2 are both 0. So, this implies the deflection y is equal to m x square over 2 E I, and what is the deflection at point 1? So, y 1, which is nothing but y of A, is simply m into A square by 2 E I, and then this thing here is your k 1 2, and see that it is same as k 2 1. So, we are able to verify the reciprocal relation. Okay. So, what could be the use of this reciprocal relation? So, you see here the pure bending case is easier. You can solve the equation and get the deflection y equal to m x square by 2 E I, right. But somebody if asks you the first problem, what is the rotation at the tip due to load at 1? So, in terms of influence coefficient, you need to know k21, correct. If you can somehow get k21, you can solve this problem, but k21 is equal to k12. So, to get k12, you simply solve this pure bending problem, right. So, that is the use of reciprocal relation. All right. Let us work out another question. So, suppose we again have the beam which is clamped and we are applying a shear force V at the tip, and we want to know theta, the rotation of the cross section at the tip. So, what is this equal to? So, can we use reciprocal relation somehow here? See, we are applying shear force at the tip. What is the corresponding displacement? That is displacement of the tip, not the rotation. So, if we want to use energy method, we would have to apply also a bending moment here m, and then the corresponding displacement of bending moment is what we want to know, theta of L. Okay. So, let us see how we can solve this problem using energy methods. So, first step was that we have to apply a dummy bending moment, so that we can write down the expression of energy of the entire beam in terms of the applied load, that is shear force and the bending moment at the tip, and then we would differentiate the energy expression with respect to bending moment to obtain the rotation at the tip, because that is the Castigliano's first theorem, right. And then finally, we have to set bending moment equal to 0, because that is the original problem. In the original problem, we only have a shear force V acting. So, the first step is apply dummy bending moment at the tip, and this was necessary because a known theta L is the corresponding displacement of m L. In the next step, obtain the energy of entire beam in terms of shear force V and the dummy bending moment m. In the third step, apply Castigliano's first theorem. Okay, that is del E by del m L, and that will give me theta L, what we want to know. And finally, set m L equal to 0 from the expression of theta L. And we do this because in the original problem there is no bending moment. No bending moment exists at tip. Okay. So, to obtain the energy, which is the second step here, we have to find out what is the shear force and bending moment at every cross section. Okay. So, if you solve this, you will get V of x is simply equal to V, and here if you set your coordinate system such that this is x that is your y and this is your z, then we have V y of x is equal to V and m z of x would be equal to m plus V into L minus x. Okay. So, having obtained V y and m z, we would then see that P, the axial force, is 0 here, V z is also 0 here, torque is also 0 here, and the bending moment m y is also 0 here. So, what is the energy of the beam? We only have energy due to shear and due to bending moment m z. So, we have integration over the length of the beam V y square by 2 correction factor k g a plus m z square by 2 e I z z, right, dx, and then we plug in the formula for V y and m z from above. And we have E equal to integration from 0 to L V square by 2 k g a plus m plus V into L minus x whole square divided by 2 e I z z dx. So, you see we have already written down the expression for energy in terms of the externally applied load, that is V and m. And now, to obtain theta L, we apply Castigliano's theorem, it is del E by del m, right. So, you come back here 0 to L 2 V into del V by del m over 2 k g a plus 2 times m plus V into L minus x into del by del m of m plus V into L minus x divided by 2 e I z z dx, and because V and m are independent, so del V by del m becomes 0, right, and this thing here that becomes 1. So, that means theta of L equals integration from 0 to L 2 times m plus V into L minus x divided by 2 e I z z dx, okay. And then we set m equal to 0 finally, correct. So, this has to be set equal to 0 and it finally becomes 1 over e I z z into the shear force phi and then integration from 0 to L minus x dx, correct. So, this is equal to V by E I z z, and when you integrate this you get Lx minus x square by 2 and then apply the limit from 0 to L, and this simply gives me V L square by 2 E I z z. Okay, so, that is how we obtain theta at the tip using energy methods. Let us work out another problem. So, again think of a cantilever which is clamped at one end and at the other end it has got what is called roller support, okay, and we are applying some force P at a distance a from the clamped end, and we want to know what is the reaction from the roller support. What is the reaction from the roller support? See, whenever we have roller support, it is free to roll horizontally. Okay? So, that means such supports cannot exert any horizontal force, because if the support exerts horizontal force on the beam, beam will exert the equal and opposite horizontal force on the support. So, then you will have some net horizontal force on the support, due to which it will start to slide. Okay. So, therefore, roller supports cannot exert horizontal force. All right. It is assumed that between the roller and the ground there is no friction. Therefore, there is no horizontal force between the ground and the roller. All right. So, bottom line, roller supports do not exert horizontal reactions. But it can of course exert vertical reaction. All right. It can exert vertical reaction. Also notice that the contact between the support and the beam runs within the paper, is not it? So, it is a line contact, that line is through the paper, and therefore, it cannot exert any movement. Okay? It does not exert any movement. About the contact line. Whenever you have line contact, the forces are distributed through the line, and therefore, the resultant of those forces about the line itself is 0, right, because they are all passing through the line. So, the roller support only exerts vertical force in this case, and our goal is to find out what is that vertical force. Now, of course, you can use either Euler-Bernoulli beam theory or Timoshenko beam theory to find out the reaction force, but we want to see how can we use energy method to obtain the reaction force. Okay. So, maybe let us remove the support and exert the reaction force on the beam. So, draw the beam without the roller support. So, we have this force P here, and then the reaction force here R, okay, and our goal is to get this R. So, the first thing to do is to write down the energy of the beam. You see, it is an energy method. So, we have to write down the energy of the beam in terms of the applied loads, which in this case is P and R, where R is the reaction force. See, in the beginning when we see it with the support, we see that we have only one force P, right, the others are supports. But our goal here is to get the support force itself. So, we have to remove the support and then draw the beam again. So, now we have two forces acting on the beam, and we will have to write down the energy of the beam in terms of these two forces. Okay. So, let us first do that and see how we then obtain the reaction force. All right. So, to get the energy, we have to first get the shear force diagram and bending moment diagram So, supposing that this is your x axis, then y axis and z axis coming out of the paper, then the shear force V y of x, that would be equal to r whenever x is greater than a, and this is equal to r minus p whenever x is less than a. So, you can get it by taking the slice of the beam and doing the force balance of the slices of the beam. Okay. What about the moment? So, for moment, if you take a slice over here and I draw the free body diagram of the slice. So, you have this reaction R, then the shear force V going downward and the bending moment M clockwise because it is negative cross section, and then you do the moment balance, let us say about this green point here. So, moment balance tells me we have minus of m plus big R into L minus x equal to 0. So, this implies the moment m is equal to big R into L minus x. Okay. And this is going to hold whenever x is greater than a. To find out moment distribution when x is less than a, we will have to take a slice here, okay, and then again draw the free body diagram of the beam. So, we have this reaction R, and somewhere here we have that load P acting, and then on this cross section we have shear force V and bending moment M, and again we do moment balance about the point in the cross section, and that gives me minus m plus big R into L minus x, right, minus P into A minus x, is not it, because this arm is A minus x, okay, and the moment due to P is clockwise. So, it comes with a minus sign. So, this has to be equal to 0. So, finally, it implies the moment m is equal to R into L minus x minus P into A minus x, okay, and this holds for x less than a. Okay, having obtained the shear force and bending moment, we can now write down the energy of the entire beam, correct. So, the energy of the beam, now because the shear force and bending moment formulas are different for two segments of the beam, we can divide the integral of the beam into two parts, is not it. So, we have integration from 0 to a, and then we have two forms of energy here, the energy due to transverse shear force and energy due to the bending moment m, correct. So, for the regime between 0 to a, shear force is R minus P. So, we take the whole square divided by 2 k g a, right, plus the energy due to bending moment, which is m square by 2 e I, and m is big R into L minus x minus P into A minus x whole square divided by 2 e I, right, and we have to take the integral of this thing. Likewise, for the second part, we have plus integral going from a to L, the energy due to vertical shear force, which is R square by 2 k g a, right, plus the energy due to bending moment. So, that is big R into L minus x whole square divided by 2 e I, and then we integrate it. All right, having written down the energy, we have to keep in mind that our goal is to get the reaction force. So, how do we get this reaction force R from here? We see that in the energy we do have the reaction force R, right, you see. Now, if we want to use Castigliano's first theorem, what do you think would be the derivative of the energy with respect to the reaction force R? So, that is nothing but the corresponding displacement of this reaction force R, but because it is a reaction force from the support, and you can see from the diagram, look at the diagram, and you can notice that at the support there is no vertical displacement, which means the corresponding displacement of the reaction force is 0. So, that is always the case whenever you have reaction forces, the corresponding points do not move, right. So, therefore, the corresponding displacement is 0, which means if we take the derivative of the energy with respect to the reaction force, that should be 0. So, that is the equation we can use to obtain the reaction force, right. So, we come back and find out del E over del R and set it equal to 0. So, when we do it, we are going to get integral from 0 to a 2 times R minus P over 2 k G A plus R into L minus x minus P into A minus x into L minus x, right, because we will take the derivative with respect to R, and we get a 2 also here divided by 2 E I, okay, and we integrate the whole thing plus the second term we have A to L 2 R over 2 k G A plus 2 R into L minus x whole square divided by 2 E I dx. Okay. So, solve it to get reaction force. Okay. Let us do another problem, but you will see that this is really interesting problem which is difficult to solve using Euler-Bernoulli or Timoshenko beam theory. So, in this case we have got a circular ring So, this is a ring which is subjected to equal and opposite forces along a diameter. So, we have let us say the force is P P, and think of points here, this is point A, this is point C, and that is your point B. Okay. And our goal is to find out by how much do points A and B get closer. Okay. Likewise, we also want to know by how much does point C move outward. Okay. Then the question could be, what is the bending moment at point C? All right. So, how do we solve this question? If you think of using beam theory, we have got a curved beam here, it is not a straight beam. So, certainly we can't use the theory that we have developed till now, and it is also a statically indeterminate problem. Think of trying to get the moment at point C. So, what can we do? So, let us divide the ring into two parts. Okay. So, we have just half of the ring here now, and it is subjected to force P at the top, and then you can guess that from symmetry the force here and here should be P by 2 and P by 2, is not it? What about the force in the horizontal direction? So, let us say I call it V x. So, how much is this V x equal to? And then the moment. So, there is some bending moment also over here. So, how much is this bending moment m? So, if you try to find it using force balance and moment balance just using statics, you will of course not be able to find out. Okay. So, that is where energy method comes into picture. It is really powerful method, and you will see its importance when we solve this problem. All right. Now, think of what really happens to this full ring when the load has acted. So, we have this full ring before deformation, and after the load acts, it is going to get deformed, and maybe it is going to become something like this. Right. So, the points here they have gone outside, whereas these points have gotten closer. Now, what can you say about the cross section of the ring right here at the point A? Is this cross section going to rotate? So, you can think, let us suppose it rotates in one particular direction, then why does it not rotate in the other direction? Right? You see, it is a perfect symmetric problem. So, the cross section at point A will not really rotate. Okay. So, it is as if it is a clamped support, the cross section is not allowed to rotate there, is not it? So, we can just think of a quarter of the ring, and then think that the top end, this is clamped, because we have figured out this does not rotate due to symmetry. Okay. So, that is the point A, and then the point C here we have P by 2, let us say we call it V y, and then we have V x also, right. We have V x and the moment m. Now, what can we say about V x? Let us think of the other quarter. So, the other quarter over here, so if the internal force and moments have the direction as shown for the top quarter, then on the bottom quarter it should be exactly opposite, right. So, it is going to be V x inward, then bending moment this way, and then P by 2, correct, which is V y. But notice V x for the top quarter, you see the center is right here, and Vx is going away from the center, whereas for the bottom quarter Vx is going towards the center. But then due to symmetry for both the quarter, Vx should have the same sense. It should be either away from the center or towards the center, but then from Newton's third law they have to be in the opposite directions. So, only way when we can satisfy both the two conditions is when Vx is equal to 0. Okay. So, symmetry tells us that Vx is actually equal to 0. So, when we put force at point A and B and push the ring, the point C here it is free to move horizontally. That is why we do not have any Vx there, okay. But it comes from symmetry. All right. So, having found all these things, we now come back to our original question and think about how to get all of them. So, for example, look at question number 2. By how much does point C move outward? To get how much does point C move outward, that is actually the corresponding displacement of Vx, is not it? So, we simply have to find out del E by del Vx, and that is the corresponding displacement of point C, right. Similarly, what is the bending moment at point C? So, what is the corresponding displacement of bending moment? That is the rotation of the cross section at point C. Now, how much would the cross section at point C rotate? So, you can see again from symmetry the cross section at point C is not really going to rotate. So, when we apply Castigliano's theorem and we do del E by del M, we simply set it equal to 0, and that equation will give me the bending moment M, is not it? So, likewise we can find everything. So, let us try to obtain them in steps. So, the first step is to get the energy of the beam. So, to do that we of course have to find out how is bending moment varying in the cross section and how is shear force and axial force varying in the cross section, right. So, let us think of a cross section which makes an angle theta from the horizontal line. So, here is that cross section, and let us take this part of the segment. So, we have this segment, okay, and it has Vx, Vy, bending moment M, and then at the theta cross section we will have shear force V parallel to the cross section. You see, it is not vertical because the cross section is inclined. So, shear force has to be parallel to the cross section, and axial force has to be along the cross section normal. So, that is P, and then the bending moment is of course like this. So, we will call it m theta, the bending moment at theta. Now, let us do force balance to get V and P, all right, and we have to recall that this angle is actually theta. Okay. So, we can draw a parallel line also here making the same angle theta. So, let us do force balance along the theta line. Okay. Let us do force balance along this direction, in the inclined direction, because that will directly give me the shear force V. So, shear force is acting opposite to this direction of force. So, we get minus of V, right, and then we have the components of Vx and Vy in that direction. So, how much would that component be? So, the component of Vx is simply Vx cos theta. Okay. So, it gets plus Vx cos theta, whereas component of Vy is Vy sin theta, and both comes with positive sign. So, this is equal to 0. So, this implies your V is equal to Vx cos theta plus Vy sin theta. Okay. Let us then do force balance in the direction of cross section normal at theta. So, if we do that, we get force P as positive, and then we have to find out the components of Vx and Vy. You see, the component of Vx is in the opposite direction. So, it comes with a minus sign, minus Vx sin theta, and component of Vy is Vy cos theta. All right. So, this is equal to 0. So, this implies the axial force P is equal to Vx sin theta minus Vy cos theta. All right. Finally, we do moment balance. All right. So, let us do moment balance about the center of the theta cross section. Okay. Now, how much is this green line equal to? So, that is nothing but r sin theta, correct, and how much is this green line equal to? So, that is nothing but r into 1 minus cos theta. Okay. So, when we do moment balance, about the center of theta cross section, then this tells me we have got minus m theta, because it is clockwise, plus m the moment at point C, okay, and that is anti-clockwise. Then the moment due to Vx and Vy. What is the moment due to Vx? That Vx times the vertical distance, which is r sin theta. What is the moment due to Vy? That is Vy times the horizontal green line. So, that is Vy into r into 1 minus cos theta, okay, and that is equal to 0. So, this implies your moment theta is equal to m plus Vx r sin theta plus Vy r 1 minus cos theta. Okay. So, in the cross section we have axial force, shear force as well as the bending moment. So, when we get the energy, it is going to have contribution due to axial stretch energy, shear energy due to transverse force and bending energy. Okay. So, the energy of the beam of the 1/4 only. So, for that we go from, you see, the 1/4, the theta varies from 0 to pi by 2. So, we have integral from 0 to pi by 2. For the shear force energy, we write down the shear force V, which is Vx cos theta plus Vy sin theta, right. So, we get Vx cos theta plus Vy sin theta whole square divided by 2 k G A plus the axial stretch energy. So, that is P square by 2 E A. So, this is Vx sin theta minus Vy cos theta whole square divided by 2 E A, and finally, the bending energy, and that is m plus V x r sin theta plus V y r into 1 minus cos theta whole square divided by 2 E I, all right, and then we integrate the whole thing, and this is r d theta, okay, because the arc length is d s and that is r d theta. Okay. And then if we want to get the bending moment at point C, then we had found out that we simply have to set del E by del M equal to 0, because the corresponding displacement, which is the rotation at point C, that is 0, right. So, we can say that set del E by del M equal to 0. So, when we do that, what are you going to obtain? You see the shear energy and the axial force energy, they do not have m in them. So, when you take the differentiation, they simply become 0. So, we have finally just the bending energy coming into picture here. So, you have 0 to pi by 2 times m plus V x r sin theta plus V y r 1 minus cos theta into the differentiation of this bending moment with respect to m, which is 1 itself, right, divided by 2 E I times r d theta, and we have to set it equal to 0. And we know that in this case V y is simply p by 2. So, we are going to put V y equal to p by 2 here, and V x is equal to 0. So, we will put V x equal to 0 here, right, and finally, we have 0 to pi by 2 m plus p r by 2 into 1 minus cos theta divided by E I into r d theta, and that is equal to 0. Okay. So, you simply solve this integral and get bending moment from here. So, you see this method is so powerful, we are able to obtain the bending moment at point C. Getting it through solving the equation is tricky, because we do not even have equation for the curved beam. Okay. Then the next question, how much does the point C move outward? So, that displacement is the corresponding displacement of V x, right. So, delta C is then simply del E over del V x, correct. So, we already have the expression of energy, and we have to take the derivative with respect to V x. Now, one approximation that we can do here is we can neglect the energy contribution due to shear force and axial force. And actually, whenever the beam is cylinder, whenever the length is large compared to diameter, or if the aspect ratio is really large, which is the case for beam, then bending energy and twisting energy, they are very significant, whereas the axial stretch energy and the shear energy due to transverse force, they are insignificant. Okay. So, we can drop the axial stretch energy and shear strain energy, all right. So, when we do it, we simply have to account the bending energy. So, it is 0 to pi by 2, and we get 2 times m plus V x r sin theta plus Vy r 1 minus cos theta, right. into del m theta by del V x, right. But what is del m theta by del V x? That is simply r into sin theta, correct, and we divide by 2 E I into r d theta, okay. And in the final expression we simply have to set V x equal to 0, okay, because we know that V x is equal to 0 and V y equal to p by 2, and bending moment m we have already found out from here, correct. So, when we substitute all of them and integrate, then we obtain the deflection of point C, all right. Likewise, you can also find out by how much do the points A and B get closer. What would that really be? That is actually half of by how much do points A and C get closer along the vertical line, is not it? So, for the quarter ring problem that we have here, we have clamped point A. So, that means now point A is not moving, but point C is going to move. So, movement of point C in the vertical direction is indeed the half of how much points A and B get closer, is not it? And what is the movement of point C in the vertical direction? That is the corresponding displacement of V y, right. So, we again have the expression of energy. You find out the derivative of energy with respect to V y, that gives you the corresponding displacement of point C, multiply it by 2, that gives you by how much two points A and B get closer, right. Okay, so, I hope you can solve this problem. So, with this I am going to close this lecture on energy methods, and in the next lecture we are going to talk about theory of failures, all right. Thank you.